Hello everybody, my name is Keelan Johnson.
And my name is Lucas Hernandez, and today we are presenting our BEAD project. What is the BEAD project? BEAD stands for Body Energy Accumulation Device. So what does this mean? So our team was tasked with designing and fabricating a device that harnessed the wasted bodily energy emitted by a Mardi Gras parade goer and turning it to useful energy. Every group was given a different customer profile, and the needs of each customer will be different, and they had to be turned into measurable metrics that each team had to meet. So a design was chosen that best fit the needs of the customer, at which point prototypes and testing began. These prototypes were reiterated upon multiple times throughout. The overall process took multiple weeks to produce an acceptable final design that meets the metrics created.
What did the client ask for? The customer's request was for a way to power LEDs on their wheelchair in a Mardi Gras parade without having to carry heavy and large battery packs. They wanted to spend several hours in the Mardi Gras parade while rolling through hot and humid and crowded streets and while taking part in the Mardi Gras parade. And they also wanted to have their wheelchair wheels generate energy which could be converted to electricity and then power LEDs. So what we needed to do to achieve this was to make our design durable, easy to use, emit enough power to power these LEDs for the user, and also be affordable for the user.
This is the Gantt chart. We used the Gantt chart to create deadlines and keep everybody on track throughout the project. As you can see here, the tasks, its assigned group member or group as a whole, the progress, and the start and projected end dates were all tracked, as you can see. The purpose was to ensure that the group was ahead of deadlines and it was clear to each other what needed to be finished and was already been completed. Time management and deadlines create priorities and achieve our goal in a timely manner.
In order to better understand our customer's needs, we needed to turn those functions that the customer requires into actual engineering specifications. So, for example, we need to turn the words that the customer says into actual target values that we can measure and compare our design to. For example, harvest energy from motion, we needed to turn that into an actual variable like more than 1 joule per mile so that we can compare and measure the amount of energy that our device exerts and compare that to the actual value and exceed that value so that our design is valuable to the consumer.
Alright, the first major document that is related to the designing and testing of our project was the objective tree. So what is the objective tree? The objective tree takes the major functions necessary for our design and breaks them down into sub-functions and constraints as seen here. So for example, one of the biggest functions of our design was efficiency. So to be efficient, you need to convert energy and need to be reliable. And then, for example, to convert energy, you need to minimize energy losses and you need to store energy. So the objective tree is a chart that shows the decomposition of necessary functions of the system and its constraints, breaking down the main requirements and the sub-functions to make problem solving easier.
And that brings us to our house of quality. The house of quality was a way for us to connect all parts of the design into one area. The who section of house of quality shows all our customers. The what's section shows all our functions and qualitative constraints. The hows shows how we will quantitatively meet each of those functions. The now section shows the competitors currently on the market. And the what's versus hows scores each function and how it is related to each how. At the bottom shows all our target values and how important each target value is to our design. So as you can see, our highest priority that we needed was energy harvesting and storage, which was ranked the highest relative among all of the other hows. So this device needs to capture and hold energy effectively above all other functions. And the strongest engineering link is that energy produced in weight drive nearly every customer watt on the left column related to how much energy is generated and how heavy the system is. And also, there are key trade-offs such as if we want to produce more energy, it's going to add more hardware, which is then going to increase more weight in the design. So there will always be some type of trade-off that you need to identify.
This is our first design alternative called LED light-up shoes. So basically how it works is that a footboard is inserted into the shoe of the Mardi Gras goer, and as the foot presses down on it, the rack on the footboard will push down on a pinion gear attached to a generator, which is attached to the LEDs. A rubber band will reset the footboard between steps for continuous operation. So its strengths are that it was the most affordable option, it would be very easy to produce, and it would be very visually festive. Although it got the lowest score because it is poor energy harvesting, a unreliable mechanism, and it just overall got the lowest score.
This is our second design alternative called the umbrella spinner. How it works is that there is a free weight attached to the rod of the umbrella, so that as the user walks and swings their umbrella, the weight will spin around the shaft of the umbrella, which will then drive a small internal generator, which can be wired to a battery pack or straight to LEDs, transferring electrical power. The strengths of this design was that it was very affordable to produce, it was easiest to manufacture, and it had positive energy storage capabilities. However, they were very large safety risks, and there was poor energy harvesting, therefore making this our second place design.
Alright, so the design alternative 3, the wheelchair generator, is one that we actually ended up choosing because of its decision matrix total score of positive 1.2, given it first place. So we'll get into it a lot more, but the overview of it is that it's a small generator attached to the arm of a wheelchair, and there's a friction roller placed on the shaft of this generator, and as the wheelchair wheel spins, it'll spin the friction roller, which will generate an electric current in the generator, which can then be wired up to LEDs, festive LEDs, of course. And as you can see, for the strengths, it was the most affordable to produce, it was easiest to manufacture, and the best energy storage capability. So it was all around a great design, but it still did have weaknesses such as possible poor energy harvesting and possible low reliability.
By using a decision matrix, we were able to compare all designs that we had came up with to a datum, which was an automatic watch. Each design was able to be scored by each group member, and the averages were taken to each function, as seen on the left side of the matrix. And each function has its own weight, depending on how important the function is to the design, as seen in the house of quality. So overall, the highest score was the wheelchair, which is why we chose it, because it had the best energy storage, the lowest cost, and it was safe. It was fairly safe, which it did have some concerns, but we were able to address those in the fabrication process.
Alright, as you can see here, this is the BEAD memo. This is the first page of 2, and what the BEAD memo was it was a 2-page document that had to be sent to our professor explaining our customer, their interpreted needs, and how we translated them into metrics, as well as a house of quality and its key takeaways. So as you can see here, as shown before, we have the interpretations turned into qualitative constraints and functions. And then we have a picture of the house of quality and a summary of it at the bottom.
And this is the second page of our memo, which shows the last parts of it, including the decision matrix, the model of the design that we chose, and the systematic improvements that we had. So it includes the decision matrix showing how each concept did and how it did or did not meet the functions needed of the BEAD project, and our best concept, and then explaining why it was better than all the other concepts and why we know it will work. And then lastly, a section that shows how the first prototype worked and how through each iteration it improved and what we did to improve it.
Engineering specs. Does our design meet the requirements? As you can see by the sample calculation provided here, we calculated the results of our product to see how they match the HOQ targets. So for example, the energy output was measured at 3,000 joules per mile, which vastly improved upon the 1 joule per mile target. The system weight was under 1 pound, which was much better than the under 2 pound target. The operating voltage barely meet the target, but it did at 4.5 volts. The cost was free because all the materials were supplied, which vastly improved upon the under 35 targets.
Here's the first iteration of our design, which consisted of a 1.5 inch diameter friction roller about the generator shaft, 3 LEDs in a series circuit. Each LED had Mardi Gras colors and crimped wire connections. The pros of this design was that the circuit lit up on the first trial and that our generator mount was resistant to damage and was reliable. However, the LEDs did not consistently light up, hinting at loose connections, and the generator did require a very fast speed in order to have enough voltage to power the LEDs. Sometimes the generator mount could be unstable, and the wires prone to being disconnected due to having crimped wire connections.
This is iteration 2 of our design, and as you can see, we removed 2 LEDs from the previous design in hopes that the voltage would be enough to light up the singular LED. We also decreased the diameter of the roller wheel in hopes that it would require a lot less speed to light up the LED. Both of these solutions did work, and it was a good proof of concept, but we still needed to improve. We soldered the wire connections, which allowed the generator to output its rated voltage, although it could not power one LED consistently, not meeting project requirements, and the design did not reliably light up the singular LED. And it still did require too high of a speed, but much less than the last iteration.
This is iteration 3 of our design. This iteration consisted of a 2 generator concept, which had a new 5-volt generator in addition to the old generator. This iteration was able to power on 2 LEDs while also having 2 0.8 inch diameter friction rollers on both generators. The pros for this design was that we were able to light up 1 more LED than the previous iteration, and also we had a greater maximum voltage output. However, the LEDs did not consistently light up due to needing both generators rolling at the same time so that voltage was being produced, and the wires were too short for the wheelchair, and the second generator mount was unstable. All this led to us changing this iteration.
This is iteration 4 of our design, and as you can see, we used longer wires so that the LEDs could be placed on the top of the wheelchair and on the desired positions. We also removed the other generator, which would have made manufacturing very complex, and although it did require a high speed to light up the LEDs and they did not consistently light up, it was much less complex than the last one. It was a reliable energy harvesting system, and it powers the same number of LEDs as the dual generator concept, theoretically.
This is the final prototype for our design. Our final prototype consists of a 0.4 inch diameter friction wheel, which increased our gear ratio from 30:1 to 60:1. We also shrink wrap all solder connections. Some things that were good about this was that we were going to be able to get consistent LED light up, even at slower wheelchair speeds. We were also able to light up more than 1 LED. However, more LEDs were desired, such as we wanted 3, and there still had to have a slight speedwalk speed needed for power.
As you can see here, our design consists of a base, a generator, a friction roller, wires, and 2 LEDs. As the wheelchair wheel comes in contact with the friction roller, it spins the generator with a high gear ratio such that it transports electricity to the LEDs to light them up. In conclusion, the BEAD project was a great introduction to the use of engineering methods for planning, conceptualizing, and fabricating a product. As a team, we agree we're overall satisfied with the result of this project, although there are some problems that we wish we could solve. We also all agreed that our skills in electronics, ideation, and problem solving vastly improved. Thank you for watching and have a good day.